So here we got a nice polynomial problem, and we are given a polynomial p of x, which is x raised to the power n plus a1 x raised to the power n minus 1 plus so on up to an, and it has roots x1, x2, so on up to xn, and another polynomial which is q of x, which is defined as x raised to the power n plus b1 x raised to the power n minus 1 plus up to bn, and it has a roots which is x1 square, x2 square up to xn square. And we have to prove that if a1 plus a3 plus a5 and a2 plus a4 plus a6 is a real number, then the b1 plus b2 up to bn is also a real number. So first I'm going to consider that a1 plus a3 plus a5 so on, and a2 plus a4 plus a6, these two quantities are real. So what we can say? We can simply say that a1 plus a2 plus a3 up to an is also belongs to real number, and we're going to use this result to prove that b1 plus b2 to bn is also a real. So let's start with this polynomial p of x. So I'm going to substitute the value 1 in place of x, so we'll obtain, okay, let me write this in form of the factor. So we know the roots of this polynomial x1, x2, x3 up to xn, so we can simply write this as 1 minus x1 multiplied by 1 minus x2 up to 1 minus xn, and this is the value of p of 1. Similarly, we can find the value, and if you see that p of 1 is nothing but the 1 plus a1 plus a2 up to an, and we know that this quantity is a real number. So we can simply say this p of 1 is a real number, and for showing this we can say this p of 1 is equal to p of 1 bar. This is the conjugate of p1, and we know in complex number, if we take the bar of any real number, then it would be equal to itself. So this is the condition when p1 is real. So we can simply write it as 1 minus x1, 1 minus x2 up to 1 minus xn is equal mod of 1 minus x1, 1 minus x2 up to 1 minus xn. And similarly we can do this for p of minus 1. So we can say that p of minus 1 is equal minus 1 minus x1 multiplied by minus 1 minus x2 up to minus 1 minus xn, and if you see, then p of minus 1 is minus 1 raised to the power n plus a1 minus 1 raised to the power n minus 1 up to an. And without loss of generality, if we let that n is even, so without loss of generality, I assume that n is even, then we can simply say that minus 1 raised to the power even would be 1 plus n minus 1 is odd, so this is going to be negative a1 plus positive a2, negative a3, and it will continue up to an. And here you can simply observe that a1, a3, all the numbers with the odd index are real, and all numbers with the even index are also real. So this whole quantity is real number. So we can simply rewrite it as minus 1 minus x1 minus 1 minus x2 up to minus 1 minus xn is equal to, since it's a real, so we can take the bar of this minus 1 minus x1 minus 1 minus x2 up to minus 1 minus xn. And if we take minus common, so we can simply cancel out and we'll obtain 1 plus x1 multiplied by 1 plus x2 up to 1 plus xn is equal to the mod of 1 plus x1 1 plus x2 up to 1 plus xn. So here we got the two equation. So this is our second one, and over here this is our first equation. And now just we have to multiply these two equations and we are done. So after multiplication, if you see in left hand side, we'll obtain 1 over here. This is 1 minus x1 and this is our 1 plus x1. So after multiplication we'll obtain 1 minus x1 square. Similarly 1 minus x2 square up to 1 minus xn square. This is equal to bar 1 minus x1 square 1 minus x2 square up to 1 minus xn square. And this simply implies that this is our q of 1 equals q of 1 bar. And if you look back to your definition of q, we can simply put the value 1 in place of x, so we'll obtain that 1 plus b1 plus b2 plus b3 up to bn is equal to bar of 1 plus b1 plus b2 up to bn. We can simply cancel this 1 from both sides, and this simply implies that b1 plus b2 up to bn is equal to bar of b1 plus b2 plus bn. And since the quantity and its conjugate are equal, so it simply implies that b1 plus b2 up to bn belongs to a real number.